discussed is there are several issues of optimization at a local as well as global level. And we start by forming a new representation, a data structure with the quads that we have, and we call it the control flow graph, which comprise nodes that are basic blocks. The property of a basic block is it has a single entry and a single exit, and it is maximal such block that or set of consecutive quads that we can identify. And then we mark the control flow between basic blocks. So within a basic block, it is always a straight line fall through execution. Now, this control flow graph can be analyzed in several ways, as we'll see. But before getting into the total analysis of the control flow graph, which involves DFA or data flow analysis, we will first take a look at the representation of every basic block, which can be used in doing some local optimizations. We saw an example here. I will not go through that again. Just to remind you that a basic block can be identified. The algorithm to identify basic block identifies a set of leader quads called leaders, where the first statement of the program is always a leader. Any statement which is the target of a conditional or unconditional go-to is a leader. And any statement which immediately follows the conditional go-to is also a leader. You can easily reason out that these are the points where the flow can change. Otherwise, at any other quad, the flow will always be the fall through. So with this, here we identify the three leaders marked as red and form this three basic blocks and the control flow graph. So on slide 13 now, the nodes of the control flow graph are basic blocks. And we'll have a directed edge from one basic block to the other. If, say from B1 to B2, if B2 can immediately follow B1 in some execution sequence. So there is a conditional or unconditional jump in the last statement of B1 to the first statement of B2, or B2 immediately follows B1 in the order of the program, and B1 does not end in an unconditional jump. So these are quite obvious things to note. And a basic block will be represented as a record, which will have the number of quads in the block, a pointer to the leader of the block, pointer to the predecessors of the block. That is, which are the blocks from where the control can flow into this block, and pointers to the successors of the block. Naturally, with the conditional jump, there could be more than one successor. And with this information, with this record structure embedded on the quad sequence, we will be able to represent the control flow graph. So this is also an example we saw where we first have the first quad, which is marked as 1. And then we have a number of blue quads, which are satisfying condition 2, that is, they are targets of some conditional or unconditional jump. So we get 102 because in quad 105 we have a go to 102, so it is a target. So in this way we mark all the quads which satisfy condition 2, and finally the condition 3 shown in gray are the quads that follow a conditional go to. So we have a if here at 102, and therefore 103 satisfies condition 3 and it becomes a leader. So having done that, then we have partitioning of the code in terms of the basic blocks and the control flow between them as shown. So while now showing the control flow, we not only refer to the sequence number of the quad, but we also refer to the number of the block to which the control is going. For example, say at the end of B5, there is a go to 204, which is the starting quad of block B3. So we will have an edge from B5 to B3, a directed edge in the control flow graph, and things will move in that way. So if little bit spread out graphically, then this is how it will look. So we can observe that within every basic block, we have a straight line flow. And we know, for example, if we look at B5, then when T8 gets 4 star I, and then later when T10 gets 4 star I, it will be easy for us to do a linear scan and conclude if I is changing in between T8 and T10 assignments. And if they don't, if the I does not, as is the case here, then I can identify that 4 star I is a common sub-expression and try to do some optimization with that. So that is our basic objective. Now, so we have, after having partitioned these basic blocks, we will now try to make a representation for every basic block so that these detections of whether a, a variable is a copy of another or an expression is common with another and so on can be understood easily. So we have a DAG representation for that, and this is a sample code that we are going to use. So here is the sample code. In the DAG representation, what we do, we create different nodes representing different expressions. And we will see what all expressions we need. Naturally, the leaf nodes of the DAG are the ones which are either constant or has expectedly a valid value when the control has entered this basic block. Others will get a value, other expressions will get a value by combining one or two nodes of this DAG. So let us just walk through the construction of this. So A assigned 10. So 10 is a constant value. So we create a node called 10 with the value 10. That is the value of the expression. And also annotate that with A to mean that this is also represented. This expression is represented. The expression 10 is represented by the variable A. Then we have B assigned 4 star A. So we have a node constructed, leaf node constructed for 4, the constant 4. And a node marked A is already there here in the from the last one. So we can say that the operation in this expression is star. So we create a node star, making 4 and 10 at the left and right child of this node. And with that, I have the expression 4 star A whose value will be in B. So I annotate this node as B. It's a pretty straightforward construction, as you can see. We get in quad 3, we get T1 assigned I star J. I and J were not there. So we construct nodes with I and J and construct a node with star. And I star J is represented by this multiplication node, and T1 gets its value, so we mark it as T1. Then in the next what I have C assigned T1 plus B. I have B as well as I have T1. So we create a node for plus operation here and make the node representing T1, which is this star node. as the left operand and this B node as the right operand. So this now represents the expression T1 plus B, which is annotated by C. Then I have T2 assigned 15 times A, which is quad 5. So we create 15 as a leaf node. We already have a node marked A. So we got the left and right operand, create a multiplication node for this expression and mark it by T2. T gets T2 plus times C. So we have a node T2, we have a node C. So we create a multiplication node and mark it by D to mean that D is T2 times C. Now we get E assigned I. Now I is already there. So what does E assigned I mean? It simply means that I'm making a copy of I in E. So whatever is the value of I at this point, value of E will also be the same. So instead of creating a new node for E, which semantically it is not, I annotate the node marked I as E. So this annotation means that a copy has been done. That is, the value of I and the value of E are the same. Then we have T3, which is E times J. And this is where I will get the benefit, because when I look for the node E, I get an annotated node, which actually is also the node for I. So we create a new node star. We do not create a new node star, because when we identify that and when we see that the right operand is J, which is also existing, and we identify that the multiplication is the operator, which already exists for this I and J, I know that this node itself will have the value that we need for T3. So again, for this, I do not create any node. I just annotate this node as T3. So which this is something which is very, very useful, and you should note here. So you can see that T1, which is I times J, and T3, which is E times J, actually happen to be common sub-expressions because E is a copy of I. So through this process of representation itself, I have detected that there is a copy here. So T1 and T3 both mark the same. Then I have T4, which is I times A. I have both I and A. So here T4, I create a multiplication node, annotate it by T4, make I its left operand, make A its right operand, which actually is 10. And we are done with this quad 9. In quad 10, finally, we have C assigned T3 plus T4. So we have T3 here, we have T4 here. But we do not have a node which connects them through any operation. So I create a plus node and mark the value of that expression T3 plus T4 as C. And which means that the C mark node that I had earlier is now invalidated. So while I do this, I will also search if there is already a C. There is already a C, but a new expression is getting created for the representation of C. So that is the reason this is the C is struck off. The earlier C is struck off to mean that C is a new assignment to this variable. This is the new assignment to the variable, and the value of C is getting replaced. Right. So by this, we have a compact representation which directly tells me three things. One is if a variable has a constant value, as you see in 10 being marked as A, that is point number 1. 2, if a variable is a copy of another, which is the node I being annotated with E, and whether I have local common sub-expression where the same node is annotated by more than one here there are two variables, so which mean that this node by itself represents both these variables. So if I proceed in a kind of structured way, then I'll be able to replace the constants, the copies, and finally the common sub-expressions in this small sequence of quads. So that is the DAG representation that we have. Now, okay, let me stop here for a while and see if there are any questions. Is there any question, friends? No question. This is pretty straightforward. Okay, so let us proceed. So we have got a mechanism by which we can identify these existence of constant values for variables, and we can propagate those constants as well as identify common sub-expression. But doing all these detections in a DAG is inefficient. It takes a long time. So what we will do is we will convert this DAG into a set of tables specifically designed to detect the factors that we want to extract from this DAG. So this is called the value numbering representation of basic blocks. So the idea is to assign a number called a value number to expression, and to every expression, and you do it in such a way that if the two expressions receive the same number, then provably they are equal on all possible values, right? As you saw in the earlier example. So we can use this to make all these deductions about constants, copies, and common sub-expressions. And these tables, there are actually three tables. There's a value number table, there's a name table, and there's a hash table. All of these are kind of either indexed or hashed, so that every operation that I need to do can be done in a very, very efficient manner. So this is what we will do: eliminate common sub-expression, do constant folding and constant propagation. And in addition, we will, in the process, we'll see that we'll also take advantage of commutativity of operators. That is, if an expression is written as I plus j, and without I or j being changed, maybe after a couple of quads it is written as j plus I, then because of the commutativity of the plus operator, these are same operation. So we will be able to identify them as common sub-expression. But of course, if the commutativity is not applicable for the operator, for example, I minus j and j minus I obviously cannot be treated as a same expression. In addition, if there is addition of 0 or multiplication by 1, we can always eliminate those. So these are the three tables which we have. One is called the value number table, the name table, and the hash table. Instead of being on this, let me take an example. Okay. So we are forming an example here, and first let us work out with our simple human intelligence. So on the leftmost column, what you see is possibly a high-level program that was given to the compiler, which is not in the 3-address form. And syntax-directed translation has generated the second column, which is the sequence of quads that I have in the 3-address code. Of course, here we are using some little bit of intelligence. Just 1 second. Sorry, I'm back. So in the second, if you see, while we are generating the quads, we are generating it little intelligently. So in some of the places, like when we have B assigned 4 star A, we have directly translated into the quad of B assigned 4 star A, while in reality, in the syntax directed translation scheme that we have studied, it will probably generate a temporary, say T1, where 4 star A is assigned, and then B is assigned that T1. So we have assumed that those kind of code generation is not happening here. We will see the handling of this later on after we have seen this. I just wanted to keep the sequence of quads small, so you can easily see, or you can later verify that the high level program is truly represented by this sequence of quads. And now let us manually do some folding, propagation, and common sub-expression. So A is defined as 10. So I can propagate this onto get B assigned 4 star 10. And when I get this propagation, then I can fold the constant, that is evaluate the constant, because this becomes a completely constant expression, 4 star A, and say that this is 40. So quad 2 changes. Quad 3 does not have any change. Quad 4, the value of B is 40, so that can be propagated right here. So I get 40. In quad 5, T2 is assigned 15 times A, and value of A can be propagated first and then folded. So I get it is 150. T2 is 150, a constant, and therefore it can be propagated to quad 6. E is a copy of I, so this can be propagated. I can do a copy propagation to get I times J. In quad 9, I have T4 assigned I times A, and A is the constant 10, so that can be propagated. It becomes I times 10. And finally, in quad 10, I have C assigned T3 plus T4, and I can actually propagate. I can actually substitute T3 by T1, because T3 and T1 both represents T3 and T1 on the third column, as you see, both represent I star times J. So it's a common sub expression. So instead of using T3, I can use T1. And after I have done these substitutions, you can see that T2 quad 5 is no more used. Similarly, T8, which is, similarly quad 8, which is T3 assigned I plus J, T3 is also not used, so these two can be removed. So we have a substantial optimization done, which is possible in this manner. So now what we'll try to do is we'll try to achieve this through this value numbering scheme of the 3 address codes of the quads. So here is on right, you can see the same code. Here there are 3 tables. Just hold on for another second. I'm sorry, getting frequent disruptions. And back. So now look at these tables carefully. In the value number table, which is hashed by name, I keep the variables that I get. And for every variable, sequentially, I put a value number, 1, 2, 3, 4, like. And I can find out the position of any variable here by hashing on the name, which is very fast. Then I have a name table, which is kind of the inverse mapping, where the entries are ordered according to the value number. And for every value number, I put what is the variable that I have. So if I have a value number, I'll be able to say what is the variable corresponding to that. And also there is a third column where I put whether the variable has a constant value. If it has a constant value, I put that. And if that field is empty, it means that the variable is not a constant. Finally, in the third table, hash table, the first column is an expression, either a binary or a unary expression. And I put the value number of the variable in which the value of this expression is currently available. Right? So I star j is 5 because I star j will be available in T1. And again, this hash table is hashed based on the expression. So here you use the expression and hash it on that. So as you can see, the name table is indexed anyway. So you don't, searching there is just an array access, whereas the value number table and the hash table are hashed on the first column to make the access really almost as efficient as of accessing an array. Now let's see how do you get the entries. And you will see that this is, there is a kind of direct equivalence with what we did with the tag representation. Sorry. So we start with A assigned 10, the first one. So as we get, A is not there in the value number table, so I enter A and put the first value number 1. It's just sequential. Put it 1. And as I do that, I entered that reverse mapping on the name table 1A. And I can see that the value is a constant. So I put the val as 10, which means A at this point is a constant. That is, whatever is value number 1 is a constant. Then I get B assigned 4 star A. B is not there in the value number table. So I entered B, put it the value number 2, enter it in the name table. It is 2. It is B. The name is B. And I know from this A, I search the value number 2. I get the value number 1. From the name table, I go to 1 and find that it is 10. So very easily by this, maintenance of these two tables, I have been able to detect that A is 10 at this point, and therefore 4 star A can be folded. So I fold and put this value 40 in the name table, which means B is value number 2 and is a constant 40. Then I have T1 assigned I times j. None of these three variables exist, so I insert them into the value number table. I gets 3, j gets 4, T1 gets 5. I also make 3 entries here. 3 is I, ignore the second entry. 3 is I, 4 is j, and 5 is T1. And this is an expression now. So I enter it in the hash table. I enter it in the hash table as I star j. And what has its value? Its value is in T1, which is value number 5. So I star j, I put a value number 5. Complete representation. So the entire information is represented. Then I get C assigned T1 plus B. C was not there. T1 is there. B is there. So C only needs to be entered. I make it the value number 6. Ignore the next entry. And in 6, in the name table, I put C. And from the name table, I can find that B. So from the value number table, I know B has value number 2. From the name table, I know 2 has a value constant, which is 40. So I just propagate that and make this as T1 plus 40, as you can see, T1 plus 40. Now this is an expression again. So I enter it in the hash table. And where will the value be found? In C, which has value number 6. So T1 plus 40 gets a value 6. So it goes on in this way. It's pretty straightforward. A is there. So I enter T2, which gets value number 7. I enter 7 here, with the variable T2. A is 10, which is value number 1. So I get 15 times 10. So with this constant propagation, I have a folding possible. So I compute 150, put it here. And therefore, 15 times A does not go into the hash table because I know that the value number 7 is T2, which is a constant 150. Then I have D assigned T2 times C. D is entered as value number 8. T2 and C can be found. So I can T2 of that value number 7 is a constant. So I propagate that. It becomes 150 times C. It becomes 150 times C. So I enter it in the hash table and its value can be found in variable D, which is value number 8. Now I get E assigned I, the copy. So I enter E because it is not there in the value number table. But I do not put the value number 9. Rather, I know it is the expression I, which is value number 3. So whatever is the value of I is the value of E. So I put it right here. So I put that the value number of E is 3 because that is the variable it is getting copied from. And therefore, now from this point, the value number 3 not only represents I, it also represents E. So I enter E as well here. So with this two entries, I have actually realized the copy that existed in E assigned I. Then I get T3 assigned E times J. E is value number 3. Value number 3 is I. That is what I'm doing now is if there are multiple entries, then I always pick the first variable in the entry. So for example, here when I'm looking for E, I get value number 3. From the name table, I get that 3 is I as well as E. So I'll pick up I because that is the first defined variable which enters value. So this becomes I times J. This now becomes I times J. As it becomes I times J, I look in the hash table that did I get it or not? Actually, for every expression, I'm doing that. I forgot to mention. So I will search if I'm getting I times J. Oh, I get I times J, which is value number 5. What is value number 5? Value number 5 is T1. So this means that at this point, T1 already has the value that is being computed in T3. So it becomes like a copy with the elimination, possible elimination of the common sub-expression. So I put T3 as a second marker in the value number 5. And I enter T3 not as value number 9, but as value number 5, because it is exactly what we did in the earliest step. But once we have got I star J, then this hash table has actually helped me get the common sub-expression and tell me that T1 is indeed same as T3 is indeed same as T1. I proceed T4 is I times A. I will enter T4, which is 9 now. And A, I know value number 1, which is 10. So I'll propagate the constant. I get I times 10. I times 10 is not there till. So I enter it in the hash table, putting the value number 9, which is T4. And finally, I have C assigned T3 plus T4. T3, I look up, I get value number 5. And the first variable in that is T1. Right? So our rule is multiple variables. I'll pick up the first one. So I pick up T1. T4 is value number 9. And so my expression becomes T1 plus T4. That is not there in the hash table yet. So I enter T1 plus T4. And where will its value be? Its value will be in value number 10. Now you can see that C is already there. But now C is going to represent a different value. This is what in the DAG we did a struck off of the C and created another node. But here we will maintain it by just adding another value number to C. Because at this point now C is representing value number 10. So we enter 10 and put the variable as. So you can see that after we have done this, we have what we have got with the manual processes. Just hold on. Sorry. Okay. Now, so this is the transform code that I have got, and we can easily tag to see that there are some variables like quads, like quad 8 here, T3, which is not used, or quad 5, T2, which is not used. That tagging can also be done along with this. So I can remove. In the next couple of slides, actually the process that I described is written down here. So when you are doing it at home, you'll be able to work it out. So going forward, I again take the same high level code, but this time I'm using a quad sequence which is automatically generated, say possibly by our kind of scheme. So instead of 10, there are 14 quads now. For example, B assigned 4 star A will typically be translated as T1 assigned 4 star A and B assigned T1. Similarly, you will have this T2. For example, here when you have I times J plus B, you will have it in T2. Then you will add B to T3. Then you will copy T3 in C, and so on. Right? So if on this, and I'll leave that as an exercise for you, if on this you do the value numbering, then this is what you will get with constants propagated, folded, and so on. So once you have got that, you can see that, for example, T1 has no further use. So quad 2 can be removed. Similarly, quad 6. Quad 7 can be removed. Quad 6 can be removed after I have propagated this. I have propagated this in. No, actually, quad 6 can also be removed because we can see that the C that was computed here has not been used any further. So I can eliminate that as well. Now, how do we get this? That this is not used any further. It is very easy. You can just do a scan in the reverse order from this, so that you know what are the variables that have been used. And when you come to a point, so you have come to this T1, and you have traversed from 14 backwards to T1. If you have not got T1 on the right hand side ever, then naturally T1 has not been used, and therefore it can be eliminated. Right? So in this way, you will see that after this elimination, it will again come back to 6 quads will get eliminated, and it will come back to the 8 optimized quads that we have got. So I would suggest that don't look at this workout, you do it yourself, and you will get a confidence on how to do the value. Okay, so let me stop here for a while and see if you have any question. Any questions? No. Simple. So the value numbering that we have learned, let us apply it to the two biggest blocks that we have got in our example. That is block B4 and block. So let's start with block B4. So here is the block B4. And if I start doing, you have a value number I1 and I1. So here I've shown it a little bit more explicitly that it does not have a value. The flag no means it is not a constant. So I is not a constant. So I get 4 star I, which goes into the expression here, and its value number is 2, which is T4. Similarly, T5 assigned A T4. So I have T5 here as value number 3, A T4 here, which is value number 3, and 3, value number 3 is T5. Then I have T6 assigned 4 star I get is 1, and with that the 4 star I, as I look on the hash table, has a value number 2, which is T4. So T4 already has that value. I found a common subexpression. So 2 is T4. Now it also gets T6. T6 also represents the same thing. So T6 gets a value number which is 2. Then I have BT6. I search with that value number 2. I do not get that on the hash table. T7 becomes value number 4, and I with that value number 4, and I have put that into BT6 with the value number. I think there is a typo here. This value number BT6 should be 4 because it's actually T7. So this is what gets generated, and we can easily see that while we are doing this, if we just keep a tagging, we can easily see that T6 was never referred to in the value number table after its creation. So which means that T6 is a dead variable, and therefore it can be removed. And after the removal, I get this sequence of code, wherein you can easily see that 4 star I, which is a common subexpression in this block, has been optimized, and you get the local common subexpression being eliminated in this process. This is a workout for block B5, which you can go through yourself and work out. Here there are 2 common subexpressions, both of which will get eliminated in the same process. So we have seen that after having done this, we have a shorter code. Now still you have a common subexpression 4 star I between block B4, block B5, and block B6, which we could not do anything about because they are not local to any one single code. And that is where we will require the global process, the data flow analysis process, to detect whether they are actually common subexpressions or not, meaning that whether say once T4 is computed and I reach T8 to compute 4 star I again, whether in between I has been changed or it has not been changed. Right? So that process we will talk about in now, besides this, we can also use the commutativity, as I said, when we are looking for I plus j in the hash table. If it fails, we should also try j plus I. If we get so that commutativity can be taken care of. If I get a quad I plus 0, I can replace it by a copy, and or y is j times 1, I can replace it with a copy and then treat the copies as we have already seen. So these can extend the scope of what value numbering can do for us. Okay, now let us point out some caveat in this analysis, which we will have to be very careful. For example, suppose AI is assigned to X and then Y is assigned to AJ, I and J, two variables used, and then Z is assigned to AI. AI is assigned to Z. Now you can see that if in the second quad we had AI assigned Y, then you would have easily, by the value numbering, invalidated that X assigned AI. X no more represents the value of AI because now it has become Y. But if not, then you cannot detect that. So there is a pitfall that you will see AI here in 1 and AI here in 3. And you might want to detect them as a common subexpression and do this optimization that X assigns Z. But the problem in that is I and J you do not know. So I and J could be the same. If I and J are the same, then this optimization is wrong. Right? So in case of arrays, we will have to be more careful. So I know that the value of AI is available in X, but the moment some assignment is done somewhere in the array, not by expression, the same expression, but from the same array, if I do some assignment, I have to assume that there is a potential that all references of I which I already know, the values that I already know, may or may not remain valid. They may have become invalid. So you kill all of them. By which what it means is that you just mark them out of the table, that these are not available anymore. Right? Otherwise, and then you make a fresh entry when you have AI assigned Z. Otherwise, there is a possibility that the code optimization will lead you to errors. Of course, if you know somehow that I is not equal to J, then AI can be using the common subexpression. And again, to know such things, you need to do the global analysis, which is the DL. As you can understand, since you have this caveat for arrays, you can create very similar caveat for pointers as well. So here you have a start P assigned to X, Q assigned to start Q, and start P assigned to Z. These two start P's may not, but they textually look like common subexpression, but semantically they may not be common because Y may have changed the same object which P was pointing to. That is, P and Q may be pointing to the same variable. So again, the same process of filling has to be. Similar pointer references and procedure calls will have to be taken care of. We will talk about more. Now, finally, oftentimes you find that the basic blocks are too small. So you may want to make it bigger to work. And while the basic blocks are just straight line flow, fall through, you can see that if your control flow graph has a subtree of basic blocks, then within that, you will always have a forward flow at least. May not be fall through, but it is a forward flow. So the forward flow can be analyzed very linearly. So you can construct bigger basic blocks. This example will explain bigger basic blocks by combining the basic blocks which form a subtree in the control flow graph. For example, here start and V1. Obviously, this is quite an obvious subtree. Similarly, V7 to stop 0, obvious subtree. But what is interesting in V2, if you do a traversal from B2, you'll see B3, B4, B5, B6. These all come on a tree. Only when here you mark them in B7, the control mark is in B7, then you have a reverse loop back. Right? So you can do a simple pre-order traversal to detect that these basic blocks form a tree. And what is the significance of being a tree? Significance of being a tree is that the flow always follows in a forward manner. There's always a forward flow. So something that happens here, say something you do in B3 cannot come back and change something in B, which actually in the total control flow graph will actually happen. So that is the part which needs DFO when you have a backward flow that is possible. So you can make this into an extended basic block and do some more optimizations, knowing that even though I may not have fall through, but I will always have a forward flow here. And since I'm taking a bigger unit, there are more optimizations that can happen out of this. So extended basic blocks are often used for this purpose. Here is a formal statement of the algorithm to find the extended basic blocks, which is very easy. It's kind of a pre-order traversal, which you can always. So that brings us to the end here of representations into control flow graph, and using that to do some simple local optimization like constant propagation, constant folding, and common sub-expressions which are local within a basic block, or if you extend it to an extended basic block. From tomorrow, we will start discussing about the data flow analysis, which is the very core of the optimization process. If there are any questions, then I'll be happy to answer. Otherwise, we'll close. Any question? Okay, then. Thank you very much, friends. We'll close here, and tomorrow at 8 we'll meet to start discussing about the data.